Hello everyone. Have you ever noticed how sugar dissolves completely in a cup of tea, making it look uniform throughout? Or how gases like nitrogen and oxygen mix seamlessly in the air we breathe? These are examples of homogeneous systems where everything is in the same phase. In chemistry, when equilibrium occurs in such systems, we call it homogeneous equilibrium. Take the synthesis of ammonia for example. Nitrogen gas plus 3 molecules of hydrogen gas form 2 molecules of ammonia gas, written as N2 gas plus 3 H2 gas gives 2 NH3 gas. Here, all species are gases, and the equilibrium is uniform throughout the phase. Homogeneous equilibria are neat and elegant because everything happens in the same medium, making them easier to analyze.
Now, let's consider gaseous systems. For reactions involving gases, we often express the equilibrium constant in terms of partial pressures rather than concentrations. Why? Because it's much easier to measure pressure in experiments than molar concentration. Using the ideal gas law, written as PV equals nRT, we can express the pressure of a gas as concentration times R times T. This allows us to define a new constant, Kp, the equilibrium constant in terms of partial pressures. And it connects beautifully to Kc, the concentration-based constant, through the relation Kp equals Kc times open bracket RT close bracket raised to the power delta N, where delta N is the difference between the number of moles of gaseous products and gaseous reactants. So, while Kc works for concentrations, Kp is the star when we deal with gases. Let's derive this relation step by step with a simple example. Consider hydrogen gas reacting with iodine gas to give hydrogen iodide. H2 gas plus I2 gas gives 2Hi gas. The equilibrium constant in concentration terms is Kc equals concentration of Hi squared divided by concentration of H2 multiplied by concentration of I2. But if we write this in terms of pressures, Kp equals partial pressure of Hi squared divided by partial pressure of H2 times partial pressure of I2. Since pressure equals concentration times RT, substituting values shows that Kp equals Kc times RT raised to the power delta N. For this reaction, delta N is 0 because we have 2 moles of product and 2 moles of reactants. So here, Kp equals Kc. Isn't that elegant? Now let's apply this relation to ammonia synthesis. The balanced reaction is nitrogen gas plus 3 hydrogen gas molecules giving 2 ammonia gas molecules, written as N2 gas plus 3 H2 gas gives 2 NH3 gas. Here, delta N equals 2 minus 4, which is negative 2. So Kp equals Kc times RT to the power minus 2. This means that under the same conditions, the value of Kp will be numerically smaller than Kc. For example, at 298 Kelvin, the value of Kp for ammonia formation is 6.8 times 10 to the power 5. These kinds of calculations show how pressure and concentration are linked in gaseous equilibria. Let's practice with a real problem. Consider the reaction 2 NOCl gas gives 2 no gas plus Cl2 gas. The equilibrium constant Kc is 3.75 times 10 to the power minus 6 at a temperature of 1069 Kelvin. Here, delta N equals 3 minus 2, which is 1. So we apply the relation Kp equals Kc times RT to the power 1. Substituting the values, we get Kp equals 3.75 times 10 to the power minus 6 multiplied by open bracket 0.0831 times 1069 close bracket. The final answer comes to about 0.033. This example shows why checking the value of delta N is crucial before converting between Kc and Kp. Homogeneous equilibria are not just abstract numbers, they are the backbone of industries. For example, the Haber process for ammonia, the contact process for sulfur trioxide, and esterification reactions in organic chemistry all rely on homogeneous equilibria. Even complex ion formation, such as ferric ions reacting with thiocyanate to give the blood red FeCN2+ complex in solution, is a case of homogeneous equilibrium. These equilibria help predict product yield, adjust conditions for maximum efficiency, and design industrial processes that feed our world. In short, homogeneous equilibria bridge textbook chemistry with real-world chemical engineering. Let's summarize what we learned. Homogeneous equilibria occur when all reactants and products are in the same phase, like gases or aqueous solutions. The equilibrium constant can be expressed as Kc in terms of concentrations or Kp in terms of partial pressures. The two are related by the formula Kp equals Kc times RT raised to the power delta N. If delta N equals 0, Kp and Kc are the same. A positive delta N makes Kp larger, while a negative delta N makes Kp smaller. These constants are critical for predicting yields and optimizing reactions in both laboratories and industries. So, whenever you think of equilibrium constants, remember, they are not just mathematical symbols. They are the guiding tools of chemistry in action. So, to wrap up, homogeneous equilibria show us the balance of reactions when everything exists in the same phase. Whether it's gases combining in a sealed vessel or ions mixing in a beaker, the concepts of Kc and Kp help chemists measure, predict, and control outcomes. I hope today's session helped you see that equilibrium is not just a formula to memorize, but a real force shaping industrial chemistry and everyday life. Until next time, keep exploring, because equilibrium is happening all around us, in every mixture you encounter.